high voltage open bus, natural frequency, vibrations, resonance, introduction. In a switchyard, aluminium tubular conductors are held between supports. When the conductor is momentarily disturbed from its steady position, it will oscillate around a mean position at natural frequency. Outdoor switchyard conductors are subjected to wind loads. They are also subjected to ice loads and, for a short duration of time, short-circuit loads and seismic loads. All these loads will act in different directions and frequencies. Of these, wind load is most significant. Natural frequency. A conductor held at either end will have a natural frequency of vibration when disturbed from its equilibrium. The frequency will depend upon the nature of support at either end. The natural frequency is given by the displayed formula. It is a function of length of span, modulus of elasticity of the material, moment of inertia, mass per unit length, type of support. Having arrived at the minimum size of the conductor and maximum span, considering corona, ampacity and mechanical withstand capability, the natural frequency can be varied only by changing the span, not exceeding the maximum permissible value. Two methods are universally adopted to change the natural frequency of vibration. Commercially available dampers may be installed at the appropriate location. These dampers shall meet the requirements with respect to the discharge for the specified rated voltage. It is the practice to install the dampers at 1/3 span plus 0.6 meters or 2 feet. Another alternative is to introduce stranded bare cables inside the conductor. Since it is inside the conductor, it will not affect the corona discharge level. It is suggested that the weight of stranded bare cable be between 10% to 33% of the weight of the tubular busbar for a given span. These cables are likely to generate audible noise. Vibration. Conductors installed outdoors are subject to wind. Apart from exerting a load on the conductor parallel to the ground, they can cause the conductors to vibrate. At higher wind velocity, they are termed as subconductor oscillation, galloping or dancing, wind sway. These occur only on strung conductors. These are characterized by low frequency of 1 cycle per second approximately, and, depending upon the span, oscillate in a vertical plane with amplitude as large as 1 meter or 3 feet. Such disturbances can cause a reduction in phase clearance resulting in flashovers. If these motions are not controlled, they can produce damage to the conductor and other elements in the transmission system. It is believed that this phenomenon occurs due to uneven ice loading on the conductor in a span. Vibration. Conductors installed outdoors are subject to wind. Apart from exerting a load on the conductor parallel to the ground, they can cause the conductors to vibrate. At lower wind velocity, they are termed as Aeolian vibration. These are characterized by high frequency of the order of 5 cycles per second to 150 cycles per second approximately, and a maximum amplitude equal to the diameter of the conductor. Conductors, when subjected to a streamlined wind speed of 2 to 15 miles per hour or 3 to 25 kilometers per hour, can vibrate at a higher frequency of 5 cycles per second to 150 cycles per second with low amplitude called Aeolian vibration. Busbars in switchyards can experience these vibrations. These vibrations are caused by vortex shedding alternately at the top and bottom. The vibration takes place in the vertical plane and the maximum amplitude is equal to about the diameter of the conductor. This can be attributed to the lift force. The frequency will correspond to the vortex shedding frequency. This is also called as the lift frequency. The vibration also takes place in the horizontal plane at twice the vortex shedding frequency. For wind speeds less than 7 meters per second, von Karman vortex shedding will induce a vertical vibration governed by the equation. Frequency equals 0.185 multiplied by the wind velocity, divided by the diameter of the conductor, where f is the frequency of vibration in cycles per second, v is the wind speed in meters per second, and d is the diameter of the conductor in meters. The coefficient 0.185 is the Stroll number. Vibrations cause cyclic stresses and can result in fatigue failure. It is prudent to ensure that the natural frequency of vibration of the bar does not resonate with the Aeolian vibration. Resonance. The conductors in an outdoor switchyard will be subjected to oscillating forces due to Aeolian vibration, caused by vortex shedding alternatively on top and bottom of a horizontal conductor due to the impact of the wind. The vibration will be in a vertical direction, with a frequency FW. vibration due to electrodynamic forces generated during a short circuit. The vibration will be in the plane of 3 conductors. The conductor will vibrate at twice the system frequency Fs. It is necessary to ensure the natural frequency does not resonate with any of the forced vibrations. It is, therefore, recommended that natural frequency is less than the system frequency, and Aeolian frequency lies in between half and √2 times the natural frequency. Several switchyards at all rated voltages exist in a country. The feedback data on their performance have been well documented and catalogued. The envisaged span for each switchyard needs to be established for its suitability for the service conditions. The span has to be kept to a maximum, to minimize the number of support insulators and to make the switchyard as compact as possible. Several software packages exist to calculate various parameters such as force, reactions, moments, stress, deflections, and the natural frequency at each node and member for the project-specific layouts and system and service conditions. This forms part of the overall study of the mechanical withstand capability of all switchyard components comprising a support structure, circuit breakers, and disconnect switches, current transformers, voltage transformers, surge arresters, and line traps. Some of the components such as voltage transformers and surge arresters are not affected by the short circuit force. Flexible connections and laminates are introduced to isolate the equipment from load transfers and compensate for the thermal expansion/contraction of the conductor. As the rated voltage of the switchyard increases, the phase spacing becomes large and consequently, the percentage contribution of the short circuit forces to the overall forces on the switchyard structure and components becomes less significant. The contribution of the self-load, wind load, and the seismic load become the governing criteria. Thank you. For a comprehensive understanding of the theory and practices of busbar systems, it is advisable to read the book An Introduction to Busbar Systems, where contents are organized in a sequence for ease of reading and facilitates cross-reference. Please procure a copy of the book with a requisition to bala@busbarsystems.net.